¿ya? Para respetar la programación.
Ok. Felipe, ¿puedes darme permiso para grabar mi propio charla aquí en mi computador, por favor?
Sí, el encargado lo va a hacer, ahí lo va a activar.
Okay. Good. Gracias. Y aunque todos los asistentes entiendan español, yo igual voy a hablar en inglés porque después quiero subir mi charla a mi canal de YouTube, donde alguna gente que no entiende español pueda entender mi charla, ¿ok? Y si hay preguntas al final, ojalá que también puedan ser en inglés, por favor, ¿ok? Thank you.
Profesor,
Yes.
disculpe, ya está grabando la charla. Yo le envío el enlace, pero ya estamos grabando en la nube.
Ok, pero la idea es, ¿puedo grabar en mi propio computador?
Me da la impresión que no, igual va a grabar en la nube.
Ok, y después, ¿cómo subo la charla a mi canal? ¿Tú
Yo
me
se la
envías?
envío hoy.
Yo se la envío hoy.
Sí, sí,
¿Me
claro, no
envías
se
el link?
preocupe. Sí,
Okay.
además, en este rato, apenas comience la charla, vamos a empezar a transmitir en YouTube y ahí ya también va a estar la charla disponible.
Ok.
¿Ya?
Good. Ok.
Ok. Felipe, si estamos listos, son las 12.
Ya.
Sí, mira, déjame comenzar a transmitir y de ahí ya inicia la presentación, por favor.
Okay, we're live on YouTube now. That's good.
Cristian, voy a presentarlo primero.
Yes.
Ya. Bueno, nos corresponde en la sala 2, el doctor Cristian González-Aviles. Él es doctor en matemáticas de la Universidad del Estado de Ohio. Actualmente trabaja en la Universidad de La Serena y algunas de sus líneas de investigación son teoría de números, geometría algebraica, álgebra, geometría aritmética, bueno, y la conferencia subplenaria 2 que nos corresponde se titula Duality, theorems for pseudo-proper algebraic groups over local function fields.
Okay, many thanks. Thanks for the invitation to speak at this meeting. So we're going to talk about duality theorems, and I'll try to be as down to earth as possible. I'll try not to make this talk too technical, okay? And so we're going to work with this field, a finite extension of this field. This is the field of rational power series. So these are quotients of power series in the variable t. Okay, over this finite field, p is a prime, it's an odd prime, or it can be 2 also, no problem. And so this field is a topological field. It's a locally compact Hausdorff field. So there will be a little bit of topology in this talk. Okay, and so this is my base field, and here I have the category of commutative. Everything will be commutative in this talk. Commutative algebraic groups over K. I will give some examples of these. And here I have something a little bit more technical, but I will try to bring it down to earth too. And this is the category of abelian sheaves. Abelian sheaves on this category, the category of schemes. Okay, if you don't know too much, very much about abelian sheaves, not a problem. If you don't know this category, it's not a problem either, because I'll try to bring it down to earth too. And so what are these? Well, these are particular types of contravariant functors. So a functor sheaf, we know what a functor is. So the sheaves in particular are contravariant functors. Okay, that go from this category. So I'll register the contravariance here, opposite category. And the target is just the category of abelian groups. So it's a contravariant functor. An abelian sheaf is a special type of contravariant functor. And this mysterious category, well, there's a down-to-earth category contained within it. So the category of algebras over K algebras, that we know. We know this one. So this guy, that's in here. Okay, so this larger category of schemes, I'm not going to use it very much, but this one I do care about, and this is quite familiar, the category of K algebras. And so every object here, every G in the category of the commutative groups, commutative algebraic groups, defines the functor, defines the sheaf. Okay, so it just means that for every K algebra R, so for every object in here, so this makes sense. It's an abelian group. In particular, we have of very great importance is the category of rational points over this algebraic group, commutative algebraic group, rational points. And so we have some examples here. Example. The finite, everything is commutative, finite K groups. Okay, and so these are these form a subclass of the category of commutative algebra groups. We have the finite K groups, and so instead of defining it as a scheme, I'm just going to worry about it as a functor. And so what's the defining property of, so what is the connection between these finite K groups and regular finite groups of finite abelian groups of group theory, you know, the things that we're familiar with? Well, the defining property, the characterization is that an object here is an algebraic group, but it has this property that if I take the points with values in a field, this is going to be finite. For every field extension. Okay, it's finite, so that's a finite K group, and I'm going to give some examples in a little bit. But note the following: that we're viewing these objects as functors over this category. So here we have the field extensions, but that's just a little bit of this category. Here we have more general algebras, you know, R over K, more general. So, but anyways, to make it finite, to qualify as a finite K group, it has to have this property. And I'm going to give an example. Example. So F is going to be the constant sheaf with values with value equal to this finite group. So this is a ZPZ. So this is a finite field. It's a finite group. And so we can define this. And what is the and so in this F of L is just going to be this ordinary finite abelian group. Okay. And of course, if I change this and I take a product of fields, it's going to be a bit more complicated. It's going to be a product of these. And if I take an R algebra, it's going to be a little bit more complicated. Okay, but that's one example. That's one. Okay. And a second one, which is also important, very important, is the functor of P roots of unity. Okay, and this one is well, does it fulfill this condition? Yeah, it does. But it's kind of boring, because if you take elements over a field and you look for the field has characteristic P because it's an extension of K. So, and so here, since P is the characteristic, then you're going to have something very boring here. It's just one, So this seems to be like then you ask, wait a minute, is this thing then really trivial? I mean, it seems to be full of air. It's just over every field, it's just one, but note, as I said before, that we're supposed to take other algebras as well, not only fields. And so if I take algebras, if I take this algebra, I think I'm up to good. So if I take this algebra, so this algebra has nilpotents, nilpotent elements, you know, and so x to the p here is 0 because I'm making it so, and so, and therefore, and then this group, this finite group is more interesting because this will give you, if you make the computations, it will give you this object because all of these things raised to the pth power give you 0. So you get, you raise this to the pth power, you get 1, but this is not 1. It's no, it's non-trivial. You know, it has lots of objects, lots of elements. So that's another example of a finite K group. These finite K groups are called infinitesimal. Okay, they have this property, but they are highly non-trivial, and they are very interesting and hard to work with. Okay, so other examples. The additive group. This is a functor. This guy does just takes the rank with the additive group structure. The multiplicative group. Here's another example. If I take this, I get this. You know, invertible elements. I mean the units. Okay, units. Okay, so that's 1, 2, 3, and this one, the abelian varieties. These are also commutative algebraic groups. And these are projective varieties. And so this group of points is compact. So it's a profinite topological group. So these varieties are so-called the proper varieties, proper algebraic groups. One particular type. These are smooth, no nilpotents on them, smooth and connected. Okay, so and what about the general object? And if I take an arbitrary element here will be a combination of these things. These examples A, B, and C are a subclass of the group, the affine groups, and the abelian varieties are projected. And any group I can, you know, produce any group here as an extension of these. So this is going to be a affine or linear part. So this is A, B, and C are examples of linear groups. This is a unipotent group, and this is a multiplicative type. These are the finite ones. So those are all affine and the abelian varieties. And so I can get an arbitrary one. I can make it. I can write it this way as an extension. It will have a largest affine subgroups in here, and the quotient will be an abelian variety. Okay, so that's how you get all of them. Okay, and so there's a classical theory of duality for abelian varieties. So every abelian variety has a duality of abelian varieties. So given an abelian variety A, you can associate to it another one of the same dimension, the dual variety, and this one, you can view it as a sheaf. It represents a sheaf, this sheaf on the flat side. And then you use a multiplicative group here as a coefficient. So these are kind of a higher dimensional character, something like that. Anyway. So you have that dual. Okay, so this is very classical. They have the same dimension. If you have an elliptic curve, it's going to be self-dual. So an elliptic curve, you can identify it with the dual. Okay, but what about the duality of affine groups? So we also have a theory of affine, a duality theory for affine groups. And for finite groups, it is very well known. Okay? It's called Cartier duality for finite K groups, like example A. You know, but you can also define the dual of this one. This is an algebraic torus. The dual is going to be a lattice, a free, of finite rank lattice, no torsion. And but the problem is that this guy, the dual of this guy, is no longer an algebraic group. It's something a little more general. It's called the formal group. Anyways, what's the definition? So this is going to be, in order to make the connection with this one, this is going to be x0. Of course, x0 is kind of a fancy name for just the homomorphisms. So here, oh, sorry, no A. I meant L. So and here you just have the regular usual characters. So this is also sheaf. These are the characters of the linear group. Okay, if you take a finite, as I said, a finite K group, then you get dual is going to be a finite. If you take an algebraic torus like this guy, you're going to get a lattice. But if you take this guy, for example, a unipotent group, you're not going to get an algebraic group. You're going to have to leave the category. It will be a formal group. Okay, so let's see some examples. So what's the dual of this guy? Z, constant. Okay, this is the integers. Okay. So what's the dual of this guy? We know this guy. Well, we also know this guy. These are one is dual to the other. Okay, good. And as I said, this guy is a little bit more complicated because it's not in this category. Okay, it's a direct limit of finite groups. It's a formal group. It's called the connected formal group. So it has the same properties as the infinitesimal ones. If you evaluate on a field, it'll give you 0. But for other R's, it's going to be more complicated. For other algebras, like in this case, Okay, good. So we have the main protagonists of the story. Okay, so and we have duality theorems, classical, well known, at least for the people who work on this area, in this area. Cohomological duality for abelian varieties, and this is a classical theorem, or classical, something very well known. It's called Milne-Tate duality. Okay, and so there is a perfect pairing of topological groups. So here we have an H1, a cohomology group. And so we have a pairing like that, and this one is perfect and continuous. So this is the perfect dual of that one. And in this guy, we know that this is compact, or profinite, more precisely profinite, and this guy is discrete and torsion. Okay, so this is Pontryagin duality. Pontryagin duality interchanges these two classes. The profinite corresponds to the discrete and torsion and vice versa. Okay, and if you're wondering about H2, well, that's not interesting. H2 of A is 0. Okay, so that's just a remark. So that one, this one will not give you anything interesting, but things change for the linear. For the linear groups, the cohomological duality for the linear groups is more complicated. Well, at least the statement is longer, and this the theorems I'm going to state are all due to Rosengarten, a young mathematician from graduated from Stanford a couple of years ago, well, 3 or 4 years ago, something like that. He's a student of Brian Conrad, or he was a student of Brian Conrad, so he found these, he proved these theorems in his thesis. And so we have also pairings here. You take the K points of this linear group, but it's not profinite. So you take the profinite completion. And then you get a duality with an H2 of this guy, which is a formal group. B, you can, of course, you can interchange these two. The proofs are different. It's not, one is not a consequence of the other. So that's why I state them separately. So these are perfect dualities. Perfect. This is profinite, discrete and torsion. Profinite, discrete and torsion. But then we get something more complicated. If you go to H1, then you get These are just Hausdorff and locally compact abelian groups, topological abelian groups. Okay, so Volkswagen duality, applies to Hausdorff and locally compact abelian groups, and so this is a bit more complicated. So that's what we have here for these are the pairings, the perfect pairings of Z Rosengarten. Okay, and so what's my problem? What do I want to do? And I hope I will have time to explain why I want to do this. But first, I'm going to just show you the theorem, the technical parts, and then I will explain the motivation behind this, because this is rather painful to do. The motivation, and I hope to finish the talk by giving you an example of how to apply these technical fireworks to the Brauer group of singular terms. So that's where I want to go. And so what's the problem? Extend, if possible, extend these dualities to the whole class, to all algebraic groups. Not necessarily linear, not necessarily linear varieties, but a mix of them. Because I can take an arbitrary commutative algebraic group, I can write it as an extension. And so I want to get, I have a duality theorem for these fellas here, and also well-known male tape duality for this guy. And I want to find a theorem for G. Okay, so as I said, this is technically rather painful. But what's the trouble for the reasons I mentioned? And so what's my first problem? My first problem is to define the dual of this guy, because I know what the dual of L is. I define the dual. These are just characters, L to the D. And the duality for abelian varieties, I also mentioned the duality for abelian varieties. So that's very old stuff, going back to Abel in 1820 or something like that. Niels Henrik Abel or Abel. Okay, so how do I find out what the right analog for the dual of this G is? Well, all I can do is apply the X function here and hope for the best, Apply this function, because if I get x0 to this guy, I know this is the dual of L. And if I apply x1 to this guy, this is the dual of the variety. So all I can do is apply the X function. And of course, I quickly realize that this is not going to work exactly. If I am stubborn and I want to stay within the category of if I want to stay within the category of algebraic groups, I'm going to fail, because the dual of a unipotent one is going to be a formal group, not an algebraic one. If I'm still stubborn and I want to stay within the larger category of formal groups, this ain't going to work either, because of this extension, this mixedness, because this is a mixed object, has a problem. So I realize that the only reasonable way to define the dual is as a complex. So I have to leave the category of one-term things and go to complexes. And if I apply the X function here, I get a natural complex, LD to AT. This is an X0 and this is an X1. So this is just a connecting homomorphism. If you apply the X function, you get a long exact sequence here with home, backwards, because it's contravariant. Home, X, and then some things will vanish, and this one will be the right analog of the dual. Okay? And of course, if L is 0, then you get the dual of the abelian variety, because this guy's not here, so you get the dual. If A is 0, you get the dual of L, and the general one is a mix. And then you have to define it as a complex, and this is a K1 motive. So this object is called the K1 motive. And it's more general than the motives defined by other people, like Deline in 74, who else? Lamont in 96, Russell in 2013. This is more general because these, this is a particular type of motive. But I'm trying to define motives in an arbitrary setting, even non-smooth. So this guy can contain nilpotence. I don't care. Okay, I'm foolish enough not to care. Okay, so but that's the technical part, and so because this is too ambitious and it's going to be very complicated, at least I want to do it for an easier, I want to do an easier problem. Do it, you know, restrict the class of possible G's. So I'm not going to do it in this talk. I'm not going to try to do it for an arbitrary G, but I will define a special class. That's of course it's something more general than linear and more general than a bigger variety, and these are called pseudo-proper. Of the title of my talk, pseudo-proper. So what is the pseudo-proper group? The abelian varieties are proper. So this abelian varieties will be a particular case of this one, but this one will not be projective. And what's the defining property? If it contains no smooth, no non-trivial, contains no non-trivial, smooth, connected, affine. Okay. So this pseudo-proper means the largest smooth, connected, and affine K group is 0. There's nothing there. But it could contain some affine groups, which are probably not smooth or probably disconnected. So it could contain some little bit of affine stuff in it. Okay, and so that's the definition. And so what about the structure of these guys? What about the structure of these guys? Well, any P pseudo-proper contains the largest abelian variety in it. So this is the maximal abelian variety inside P. And the quotient is going to be a group, which I call a Q, which is the quotient, okay, that will not contain any abelian variety or any torus, any algebraic torus. So it will be an extension. It will have a unipotent quotient, and the kernel will be a finite K group of multiplicative type. For instance, this guy could be a mu n, for example. So this is a finite K group. So, okay, so this is the definition. Okay, the definition. And if this guy is connected, because I'm not assuming it is, if it's connected, then this guy is going to be infinitesimal. This one, in that case, that this guy will be something like this one, mu p. Okay, it will be an infinitesimal group. It will, you know, you take the rational points with values in the field, and it will be nothing. It will be trivial. So it will be of that type. If this guy is connected, and also smooth, then this guy is 0. Then in that case, you get a class of the class of pseudo abelian varieties defined in 2013. So you get the pseudo abelian varieties. Pseudo abelian. Okay, so there's a subclass of the class of the pseudo-proper. The pseudo-abelian varieties of Potaro. Potaro introduced them. He discovered or created them. Actually, he discovered these objects that are very important. And okay, so and I have the theorem, the duality theorem for these objects at least. That's what I wanted to present in this talk. Just the duality theorem for these groups, not an arbitrary G, but just for this class. But you know, it's some progress because I'm not assuming that everything is smooth. I'm not assuming I'm going to state my theorem for pseudo-proper. So they could be, this guy could be disconnected or not. Could contain some secular stuff, non-smooth, some nilpotents. So it's more general than pseudo-abelian varieties. And so what's the theorem? So let P be as above. Pseudo-proper, and I will assume that this P, I can write it, well, I can always write it like that, you know, because it's an algebraic, it's an object in CK. I said before. I don't want to call this L because it's not as general as the case of G, you know. So I call it J, but this is affine, and this is not being variety. But this guy cannot be smooth because P contains does not contain any smooth connected affine. So this guy is going to be, in general, if P is pseudo-proper and connected, for instance, you can always do this, even with J connected, but it cannot be smooth because it cannot be smooth and connected and non-zero by definition. So of course, I'm going to avoid trivial cases, not an abelian variety, because otherwise I would just be rediscovering the Milne-Tate duality theorems, you know. So not an abelian variety. So it's pseudo-proper. They can write it like that. And J will be non-smooth, in general non-smooth. Okay. And I can define the dual K1 motive. So, oops, sorry, this is going to be J to P. So that's what plays the role of the dual. And so I have my pairings here. These pairings generalize Rosengarten duality and Milne-Tate duality, at least for these particular types of groups. So I get this guy's profinite. You know, K rational points here, and I get an H1. So this is a hypercohomology group because this is a complex. Okay, but still it's an abelian group. And so this is perfect duality. This is profinite. This is discrete and torsion. And the one I care about is B because B is the one that is connected to my with my applications to the Broward group. Okay, so this one, since if P were smooth, this one would be discrete and torsion, but P is not smooth in general. Okay, because this guy can be non-smooth. So this will not be discrete and torsion. It will just be Hausdorff and locally compact. Therefore, this will not be profinite in general, but it will be Hausdorff. We'll see. Okay, if I have the time, we'll see that it's Hausdorff and locally compact. Okay, so as I said, I do care about B more than about A for reasons of time, you know, time constraints, but also because of my applications towards the end. So that's a duality, my duality theorem for these pseudo-proper groups. It's not working today. It's not working today. Okay. So what about this group here, which I really care about, as I said. So how weird is this? How strange is this group? Well, it's not too bad because I get the K rational points of the abelian variety mod out by this guy. This guy turns out to be finite. So this is a quotient of the profinite group by a finite. So this is profinite. And it's Hausdorff because this is finite. So this is closed in here. This is Hausdorff. And here I get, this is the type of group that Rosengarten worked with. And here we get H1KAT. So we got something familiar. But you know, it's a mix. This guy is a mix of a profinite group and this group, which is Hausdorff and locally compact. It will not be profinite. It is profinite if J is smooth, but you know, J can be non-smooth. And so that's the, you know, brings it down to it, you know, gives it some, we can understand a little bit better because of this exact sequence. You know, it's something rather well known, something that Rosengarten worked with, but it's a mix of those two things. Okay, and of course, I can do it if I have the time. Yes, I think I do. Not very much time, but I have a remark. I can apply. Say, if I take any G? Okay, any G. The good thing is that any G can be written as an extension of this different type, where I can assure that this guy is. I can be sure that this guy is smooth. Actually, this N is going to be the largest smooth connected subgroup here. And the quotient will not be an abelian variety in general, but it will be pseudo-proper. Okay. So what I'm trying to say is that this theorem is like a stepping stone to try to get a duality theorem for this guy in general, using the simplifying technical fact that this guy is smooth now. So you see, this guy J can be non-smooth, but this one will always be smooth, and so it will make things simpler. And of course, this sequence gives rise to a sequence of K1 motives, the dual sequence, and this will be the usual dual of an affine group, but it will be placed in degree -1. So, and here I have an exact sequence of complexes, and I have a duality theorem for these guys. For this, by Rosengarten, I have a duality theorem for this, and also this one gives me a theorem for this one, and so I can get to this guy. So, see, this is not only a specific theorem for a very specific class of groups, but it's also useful to attack the more general problem. But I don't have the time to talk about this, of course. But I do have the time to give my example. Okay, finally, prior groups, singular curves. It's all this technical, technical effort. What is this technical effort leading to? I've been working on this for months. It's not easy because I have to check that the topology, the algebra is not so much of a problem, but the topology you have to check. I have to verify that every function, every map that I come up with is continuous, because otherwise things will not work. It has to be continuous and strict. It means it has to transfer the topology the right way, because otherwise contrarian duality does not behave well. So I have to check that they are continuous and they are strict. And also I have that this sequence induces an exact sequence of groups algebraically, but I have to check the topology as well. So that's a pain. Anyways, that's why it's been taking so long. Okay, but the example is here. Finally, the example down to earth. And I'm going to start with this curve. So for people who know about elliptic curve, this is some resemblance to elliptic curve, but it's not an elliptic curve. And this is a regular curve, and but it's affine. Okay, so you have the variable. Remember that my field is this guy, an extension at least. Well, in this case, I'm going to consider just the simplest possible. Even in that case, it's difficult. Okay? The simplest possible over that field, the rational local function field. So I'm going to take this curve, and this is affine, and I'm going to take the regular compactification. So it will be regular, but it will be compact, so proper or compact. And the problem with this guy is that if I view it over the algebraic closure, it's not regular. So this is a singular curve, because even though over the base field is nice enough, it's regular, no singularities. But if you go up to the algebraic closure of this guy, because this guy is not algebraically closed, you have to take the algebraic closure, and it's an imperfect field. So you see, this T is not a Pth power, because this is imperfect. But if you go up to the algebraic closure, this guy will become a Pth power. And since P is the characteristic, you will get a Pth power in here, and after some changing of variables, you get a cusp. So this curve acquires a cusp. Okay, it's singular. Acquires a singular point over the algebraic closure of this type. So this is a non-singular. It is a singular curve. Okay, and so I'm going to define just P. It's going to be the Picard scheme of this, because this is compact. So this guy is an algebraic group, and I'm going to take the connected components. And this is connected, and since we're in dimension 1, this is smooth and connected. And why do I call it P? Not because of the Picard scheme. It's because this guy's pseudo-abelian. It's not an abelian variety. It's a pseudo-abelian. This is an example by Totaro, based on an example of Rosenberg from the 50s, okay, or derived from it. And so, in this guy, therefore, it's an extension of this type, and the abelian variety here, the quotient abelian variety, this is an elliptic curve. Okay, elliptic curve, good. Elliptic curves, I know. These are one-dimensional abelian varieties, so not too bad. You might think it's not too bad. But... And what about the J? This is linear. It contains a finite subgroup, and the quotient is unipotent. And we know this guy is the what I called QM before. So this is multiplicative part. And this guy has dimension p minus 1 over 2. So this guy has dimension p plus 1. P plus 1 over 2. So 1, p minus 1 over 2. You add them up to get this. Okay. So that's unipotent. And I can prove that there exists a pairing between the prior group and a homology group. This is called Van Hamel homology. This is a homology theory created by Hamel in maybe 2001, something like that. Sadly, Van Hamel is not with us anymore. He passed away 2008, I think. He's a very tragic, very brilliant young man who left us way too early. Anyways, his legacy, part of his legacy is homology. And so I can prove that there is a duality, a pairing, perfect pairing. This is a more general version of Lichtenbaum duality for singular curves, because Lichtenbaum did it for smooth curve over fields of characteristic 0. I'm working a characteristic, positive characteristic, this guy non-smooth. Okay, so okay, so this guy, I'm almost done, so please be patient. This guy, there's a natural degree map to Z, so the meaty part, I mean, the important part here is the kernel, so the degree 0 part. The elements here that have degree that go to 0. So this guy, how is this guy related to my P? Okay, so I got this, and this guy, but this guy is a subgroup. This guy is a subgroup of my group. Finite index. Finite and computable index. I can compute the index. And so this is a large subgroup in here. And so this guy is my the group I mentioned before, the one that was an extension of, but this guy's going to be an extension of the k rational points of the elliptic curves over a finite subgroup, and then will be an H1 of the dual of the JD, the dual of the character group of that one. And so that's why I'm doing all this, because I want to get to this fellow via duality. So this guy is intimately connected with the dial group by duality. And that's what I want to talk about. And I thank you for your patience. And I spent exactly 40 minutes as I promised. Thank you.
Any questions?
Okay.
Okay. In the name of the organization COMCA, thank you so much, Mr. Christian.
Christian. Many thanks for your patience.
Muchas gracias, doctor Christian, por la presentación. Bueno, si alguien tiene duda, también la puedes plantear en español. No.
Yes. If you want to ask in Spanish, you can do. You go ahead and I can translate.
Bueno, entonces se da por finalizada la sesión. La programación se encuentra en la página y en las invitaciones que llegaron a los correos. A las 3 de la tarde comienzan los cursillos y agradecidos por la asistencia.
Okay.
¿Ya?
Thank you.
Gracias.
Okay, bye. Hope you send me the video. Okay, please.
Ya, sí, le voy a recordar a Ramiro, que es el encargado. ¿Ya?
Good. Okay, bye bye.
Chao.